Chapter 11, and we're starting to talk about electrons, really. And the main kind of focus, as we'll continue to talk about today, is electrons as they sort of transition from, say, lower energy levels to higher energy levels. The arrow represents an electron, and these are energy levels. In order for them to go up to a higher energy level, the atom has to absorb energy, and that's going to cause those electrons to be what's sometimes referred to as being excited, and they will jump to a higher energy level than they started with. As a result of that, most things in chemistry like to sort of be in the lowest state energy. That's really the more stable sort of situation. So what happens is eventually these electrons will kind of work their way sort of back down. And as they work their way back down to a lower energy level, that's going to be an exothermic process for the atom. It's going to release energy to allow those electrons to go from a higher energy level to a lower energy level. The result of that is the energy is usually released from the atom in the form of a wave. And a wave, as we talked about, has a few characteristics. Between two peaks is what is known as lambda, or the wavelength. Also, between two troughs as well is the wavelength. We also have the frequency, which is sort of that new symbol there, which is frequency. And frequency is usually reciprocal seconds, are a hertz. They are a one-to-one relationship between those two. So one reciprocal second is the same as 1 hertz. Wavelength, by the way, is typically given in meters, sometimes centimeters, and a lot of times nanometers. And nano, again, is a common sort of conversion, which is that 10 to the minus 9. We could use this relationship to calculate the wavelength or the frequency of a wave if we know one or the other by using c is equal to the wavelength times the frequency. C is a speed of light, which is a constant. And again, a lot of places will use 3 times 10 to the 8. But here they do want you to use, I believe, 2.9979 times 10 to the 8 meters per second. And again, that's something that you should know. And because that's a constant, if we know the wavelength or we know the frequency, we could calculate the other. When you are using this formula, the wavelength does need to be in meters for everything to cancel out correctly. So the wavelength definitely should be in meters, and the frequency should be in reciprocal seconds. Thank you. For everything to cancel out correctly. Um, there's also a relationship that I believe we talked about as well in terms of the wavelength and energy and frequency. So if you have a longer wavelength, you typically will have a lower frequency, and that usually is a result in lower energy. And if you have a shorter wavelength, usually will have a higher frequency, and that usually results in higher energy. So as these electrons transition from one energy level to the next, the atom will typically, especially if they're going from a higher energy level to a lower energy level, the atom will release that amount of energy. As we'll talk about here, depending on the wavelength of that energy, for example, it could be in the visible part of the spectrum where we see colors. So you might see, red, orange, yellow, green, blue, indigo, violet. It may be outside that sort of area of the spectrum as well, where we might not see color. Like, for example, in today's lab, we will see color as you do that basically in flame tests. You'll see some color basically occur as those electrons start jumping energy levels because that happens in the visible part of the spectrum where we can see them. Now, the other sort of idea that we talked about as well, and we'll continue, I think, to talk about in this chapter, is the idea of how electrons and energy and atoms are sort of released and absorbed. Is this idea of quantized energy? And the idea of quantized energy is basically is sort of that staircase example we might have talked about last time. And the idea is much like stairs, you will find yourself either on sort of this step, or that step. No matter which way you're going, either up or down the stairs, you're going to find yourself somewhere on one of those steps. Again, you don't typically lay up halfway between steps because you're going to fall, right? And you're not going to be able to be there any much longer. And electrons travel from energy levels in the same way. So electrons will either gain enough energy or lose enough energy to completely make that transition from one energy level to the next. So for example, here, if we had this electron up here and it wanted to come down, it would lose enough energy to fully make it to, say, that energy level there. It will never find itself like between energy levels, just kind of hanging out and stuff like that. So it always sort of gains or loses energy, and what's sometimes referred to as discrete packets of energy, which are known as a quanta of energy. And that's the idea there. It's definitely enough energy to make it fully from one energy level to the next, enough energy to go from multiple energy levels to the next. They'll never sort of find themselves in between. Any questions on any of that there? All right. So I think we finished up on an example. So think about the next example here we didn't do. So why don't you give this one a go? We're looking for the wavelength in nanometers for a wave with a frequency of 5.6 times 10 to the 14 hertz. Once again, that nano conversion you should know is 10 to the minus 9. So take a few moments there, work it out, see what you come up with. Okay, let's take a look. So obviously here we're going to use our formula there. Our C is equal to our wavelength times our frequency. In this particular case, remember a hertz is a frequency, so that is 5.6 times 10 to the 14 hertz. Also remember that 1 hertz is the same as 1 reciprocal second. So the units here can also be reciprocal seconds, either one you want to go with, it's the same thing. We are looking for our wavelength, which is our lambda. We do have C always, never usually given to you in a problem. It's that constant 2.9979 times 10 to the 8 meters per second. And again, that's why obviously this reciprocal seconds works here. We're going to solve for our wavelength by dividing frequency to the other side, and that's going to give us C divided by the frequency. The good news on this rearrangement of this formula is it's always the speed of light divided by the other thing, so the wavelength or frequency. Here we'll put it in 2.9979 times 10 to the 8 meters per second divided by our 5.6 times 10 to the 14. Once again, this is the same thing as reciprocal seconds or hertz. Those seconds will cancel when we divide, and we will end up with a number here of 5.35 times 10, and I want to say 7. So negative 7 meters is the units here. We are looking for nanometers. So remember our nano conversion 10 to the minus 9. So that means in one of the prefix units, there is 10 to the minus 9 meters. So again, you want to make sure you use that in the correct fashion. Also, you definitely want to make sure you're using your exponent button when you punch these into your calculator. We'll take our 5.35 times 10 to the minus 7 meters, doing our conversion 10 to the minus 9 meters, 1 nanometer. Remember that 10 to the minus 9 is basically 1 times 10 to the minus 9 if you need to put it in your calculator that way. So if we do our conversion here, we will end up with 535 nanometers. Technically speaking, 2 sig figs there. So I guess we could round that up to 540 nanometers in this particular case. Any questions on that one there? So like I said before, the good thing about this calculation is pretty much the same calculation. Always speed of light up on top divided by the other thing. So if you have the wavelength, that will get you the frequency. And if you divide by the frequency, that'll give you the wavelength. Any questions on that there? Now, speaking of waves coming off when electrons transition, when they do transition, those waves coming off in the form of a photon of light will have a specific wavelength, and they will fall somewhere here on the electromagnetic spectrum. And the electromagnetic spectrum here, as you can see on the right-hand side, or at the top here, we have wavelength, and on the right-hand side, that's 10 to the fourth, which is a larger wavelength. On the other side, that is 10 to the minus 12 in terms of the wavelength, and that is a much smaller or shorter wavelength. So remember our relationship in terms of wavelength, frequency, and energy. On the right-hand side, we have a larger wavelength, which means we have lower energy on the right-hand side here. On the other side, we have shorter wavelength, which means we have things with higher energy. So depending on that energy of light that's coming off or that wavelength of light that's coming off, it'll fall somewhere here on the spectrum. And again, you do need to know the electromagnetic spectrum here. You need to know the different parts of it. So here we have that here in this area, we have radio waves, kind of larger wavelength, lower in energy, right? So as we may talked about last time, right? Turn your radio in your car to a specific frequency and it sends the radio waves in to your receiver. Going to the left, we then have microwaves, so a little bit more energy, enough energy to spin your water molecules in your food really fast. And you get like a pizza in like 2 minutes. It's not too bad. Coming next afterwards is the infrared part of the spectrum. The infrared part of the spectrum, where you feel kind of heat and stuff like that. After that, again, getting shorter in wavelength, higher in energy, we're going to hit some visible part of the spectrum. That again is where we see color. And this is our kind of Roy G. Biv happening here, right? Red, orange, yellow, green, blue, indigo, violet. So our Roy G. Biv coming through there. And obviously, if the energy coming off from the transition of those electrons falls somewhere within that wavelength spectrum there of the colors, the visible part of the spectrum, we will see colors. Now, even with colors, there is a difference in energy. So if we just look at our outside ones here, this is red, which is 7 times 10 to the minus 7. That is a larger wavelength and lower in energy. Then if you come to the other side of the spectrum there, 4 times 10 to the minus 7, that is a shorter wavelength and higher in energy. So red light is actually lower in energy than, say, purple. And obviously, as you go from right to left there on the colors, we're going from lower energy to higher energy. So even within the visible part of the spectrum where we see colors, there is a difference in energy. And energy is obviously increasing towards the purple color there on the left. Coming next, a little bit shorter wavelength, higher in energy, is ultraviolet. That is UV, right? Why we put sunblock on so we don't get too burnt when we go outside, right, from the UV rays. X-rays, even shorter wavelength. Again, why they throw a lead vest on you and leave the room when they shoot the X-ray, right? Because there's a little bit more energy. And all the way at the end there are gamma rays. And gamma rays are just basically pure energy. We talked about them when we talked about the atom. That is basically very, very high energy radioactive rays. And you need a lot of protection, obviously, if you ever use anything as a gamma emitter. So, as I mentioned before, as these electrons transition, the wave may come off in the visible part of the spectrum where you would maybe notice some colors, but it can come off in other parts of the spectrum where you may not obviously notice color as a result of it. You do need to know the electromagnetic spectrum here. You need to know it in its order and including colors. And you need to know it based on, which one, say, has a shorter wavelength, higher energy, higher frequency, that sort of relationship. I don't know if I'll ask you the exact numbers. I probably won't, but you need to be kind of able to put them in order based on things like that, like shorter wavelength to higher or lower frequency to higher. Any questions on that there? And that also includes the colors as well. So as we've been talking about, atoms and molecules basically emit or absorb energy, and these really discrete quantities of energy are packets of energy, which again is sometimes referred to as a quantum energy. And we could actually calculate the energy related to a wave, and we could use this equation here. That is E is equal to H times the frequency. H is Planck's constant, which again is another number you need to know. That is 6.63 times 10 to the minus 34 joules times seconds. That obviously is that. That is our frequency. It does need to be again in reciprocal seconds. And the energy that you'll end up with here will be in units of joules. If you just look at the units, you're going to take joules times seconds times a reciprocal second. The seconds will cancel, and that will leave you basically with units of joules in this particular case. Now, this energy relationship here, or that formula there, will energy if you know the frequency. Now, tying together the previous formula that we saw, which is C is equal to the wavelength times the frequency, if we were to solve for frequency by dividing that to the other side, that would give us the frequency is equal to C divided by the wavelength. And since that formula on the bottom there is E is equal to H times the frequency, we could substitute that in, and we get this version of the equation, which is the energy is equal to H times C divided by the wavelength. Now, the two top numbers are both constants. So what that allows you to do is, if you know the wavelength, you can calculate the energy by using this formula. So if you know the wavelength, you could calculate the energy. And obviously our original one here, if you know the frequency, you could calculate the energy. So really, if you want to calculate the energy of a wave, you just need to know one of those two things, either the wavelength or the frequency, and you can calculate the energy associated with that particular wavelength of light. Now, a reminder in terms of units, these obviously are constants, these two values. Those are those constants. But in terms of units of the wavelength, it does need to be in meters. So if you're using this equation, the units there, wavelength, does need to be in meters for everything to cancel out. So that does give you a couple different ways to calculate the energy. And again, you pretty much just need to know one of those two things, wavelength or frequency, and you'll be able to do so. Any questions on that there? Yeah. All right, so why don't you try it there? What is the energy associated with a wave that has a wavelength of 465 nanometers? So okay, so let's take a look. So here we're looking for the energy. So we have E is equal to H times the frequency. In this case, though, we do have the wavelength given to us, which is 465 nanometers. Obviously, we're looking for the energy. So in this particular case, we kind of need to tie the other formula together like we just talked about. Here, once again, solving for the frequency is C divided by the wavelength. Taking that and substituting that in will give us E is equal to HC divided by the wavelength. So H, once again, is Planck's constant, which is a constant of 6.63 times 10 to the minus 34 joules times seconds. C is obviously our speed of light, which is also a constant, 2.9979 times 10 to the 8 meters per second. So that is that. That is that. We have the wavelength, but once again, a reminder, when we do use it in this formula, as I mentioned, it does need to be a meter, so we do want to do that conversion. So our nano is the same one that we just used there, 1 nanometer, 10 to the minus 9 meters. So we'll do that conversion. 465 nanometers. In this case, we're going to go 1 nanometer on the bottom, 10 to the minus 9 meters up on top. The nanometers there will cancel, and we will end up with 465 times 10 to the minus 9. That's going to get us there. Yeah, 4.65 times 10 to the minus 7 meters. And again, we need to use that because our speed of light's in meters, so everything cancels out correctly. So now that we have everybody in the right units, we'll pop it in there. E is equal to our H, 6.63 times 10 to the minus 34 joules times seconds, times our speed of light, 2.9979 times 10 to the 8 meters per second, divided by our wavelength in meters, 4.65 times 10 to the minus 7 meters. In this case, the meters on top and bottom will cancel. The seconds will cancel on both of those. And that's going to leave us joules. That's the only thing left. We're going to use our exponent button for sure. 6.63 exponent negative 34 times 2.9979 exponent 8. We're going to hit equals divided by 4.65 exponent button negative 7. Going to get us here 4.27 times 10 to the negative 19 meters in this particular case. Not meters, I'm sorry, that's just joules. Sort of like meters if you want the wrong answer. There you go. Let's try that there. That's why they invented erasers, I think. There you go. Joules. Any questions on that calculation? So like I said before, just need the wavelength or the frequency, and you can figure out the energy. The key on most of these calculations, a lot of times is units, and make sure that the wavelengths is always in meters, or you kind of go into the formulas. Very commonly, you will have them in nanometers and stuff like that. Any questions on that calculation? Okay. All right, try this one here. What is the energy associated with a wave that has a frequency of 2.8 times 10 to the 14? All right, so in this particular one here, again, we're looking for the energy. So we'll take our equation, E is equal to H times the frequency. In this particular case, we were actually given the frequency, 2.87 times 10 to the 14 reciprocal seconds. Once again, H is a constant that you always have, again, but never given to you in a problem. So 6.63 times 10 to the minus 34 joules times seconds. Just got to plug and chug into this one here. So a little 6.63 times 10 to the minus 34 joules times seconds times our frequency, which is all good to go. It's all in the right units. Again, the seconds will cancel in this particular case, going to leave us joules. So 6.63 exponent negative 34 times 2.87 14. Going to hit us a 1.90 times 10 to the minus 19 joules in this case. Any questions on that particular one there? Okay, so let's continue on. So as we've been talking about again, and what we've been calculating is the energy associated with, again, a photon of light as an electron transitions. So you can see an excited lithium atom will have its electrons in a higher energy state. As it kind of goes back down to a lower energy state, again, we're going to be giving off that energy in the form of a photon of light. Now, one of the theories here of the hydrogen atom was one done by Bohr. And Bohr's theory of the hydrogen atom, as we'll talk about, works really well to describe sort of what happens with hydrogen because it has only one electron. But as you move away from hydrogen to atoms that have more than one electron, it doesn't really hold up all that well. But it does describe some of the features that we do see with the hydrogen atom. And part of that is the idea of what is known as an emission spectrum. So an emission spectrum is basically what happens when electrons sort of relax back down to a lower energy level. The atom itself is going to emit this amount of energy, and that energy again will correspond to some specific wavelength. Now, the way you can get an emission spectrum is you usually have to sort of excite the atom, add some energy to the atom. Obviously, for example, like we're going to do later today, when you put your substance into the flame, you're clearly adding a lot of energy to it. You could also do this with an electrical current. high electrical current, kind of like a neon lights where you kind of see neon colors. Basically, high electrical current going through the gases there is going to give off a certain amount of color. And when we look at, for example, a sort of metal that's in a hot energy source or a high temperature source, it will glow. And that visible glow is part of the spectrum where we could again kind of see color with the eye. We could also feel warmth coming off of it. And again, that is part of the emission spectrum, the electromagnetic spectrum we saw more like the infrared region. Now, a common feature of the emission spectrum of the sun and heated solids is what is referred to as a continuous spectrum. So one type of spectrum is a continuous spectrum where basically all the wavelengths of light are represented within the spectrum. So sort of the difference between sort of a continuous spectrum and what we'll talk about shortly, which is a line spectrum, is how the energy is happening. The sort of coming off. So if you remember my earlier example, we were talking about stairs. That is not a continuous spectrum because you're at one step, next step, or that step. You're not in between. You're nowhere along the way. So you could think of a continuous spectrum as occurring when, for example, if you walked up a ramp, for example, instead of stairs, you basically could stop anywhere you like up that ramp, right? There's no problem doing that. You're not going to be like a step. If you stop in between two steps, you're going to fall. But if it's more like a ramp, you can pretty much stop wherever you want. That's going to allow all kinds of wavelengths of light to occur at the same time. And this sort of continuous spectrum that occurs with the sun or things sort of lit by the sun and also heated solids. Now, the emission spectrum of atoms in the gas phase do not show this kind of continuous spread of wavelength. We see a more what is referred to as a line spectrum. And a line spectrum is pretty much what the name implies. It is basically distinct colors. I'm going to change the colors here. Happening at distinct wavelengths. So you see these lines that occur at different sort of wavelengths and different colors. And they're distinct based on the colors that you see. They're also distinct at the energy or wavelength at which they do occur. So we don't get this sort of continuous spectrum like a rainbow of everything kind of coming out. We get these distinct lines. And this is because this is how electrons sort of transition in this type of situation. They transition, as we talked about, in this quantized energy. And that quantized energy means, again, like the staircase, they could only be at certain energy levels. And because those electrons could only be at certain energy levels or really transition between certain energy levels, there's a fixed amount of energy that will always occur as they make those transitions. And because there's a fixed amount of energy, just like our calculations we just did, those energies will correspond to a specific wavelength. And at that specific wavelength, you will see, for example, a line of light at a specific color, especially obviously if it's in the visible part of the spectrum. So each of these sort of colored lines that you would see represents electrons transitioning from, for example, maybe the fifth energy level to the third, just that electron transitioning from there, or maybe like the fifth energy level down to the second. That will give you another type of line, or the fifth to the fourth energy level transition will give you another type of line. The elements themselves have such a unique spectrum or line spectrum that based on the lines that you see, the wavelength that they occur, you can identify what element you're looking at based on the kind of line spectrum that occurs, because they are these very specific quantized transitions that occur as the electrons move from one energy level to the next. Any questions on that there? And you could see these lines typically by looking through a prism, and it will separate out the light. And you can see the difference here in a continuous spectrum, which is like what we got going on there up on top. you can kind of see we get almost like a rainbow. Everybody's coming off at once. Again, this is more of the walking up a ramp type situation. You pretty much can stop anywhere along the line. Here on the bottom, we have our electron discharge tube. Again, as it goes through the prism, it's going to separate out into distinct lines with distinct colors and distinct wavelengths, giving it a line structure, again, corresponding to more of that quantized energy. Again, those electrons are going to be either here, 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 or they may be here and they may transition to here, it may transition to there. Once again, they will always sort of gain and lose energy enough to make that certain transition of energy levels. And that's going to result in the different colors that you see. You could also, just by looking at some of the colors, as we will see, for example, this color is closer to the red side, right, of the visible part of the spectrum. And red is lower in wavelength, right, and lower in energy, as opposed to, say, this purple line that we see over here, which is on the shorter end of the visible part of the spectrum, which is higher in energy. So you would expect perhaps a transition of purple happening maybe a lot of energy levels, right? Because the difference between where it started and where it ended would be a greater amount of energy. The result of that would be a shorter wavelength and more of that violet color, as opposed to this side where maybe what we're seeing is the electron just transitioning one energy level, which would give you a much longer wavelength, lower energy sort of color that actually happens. So again, by just looking at the colors, you can make a relative prediction of, how far perhaps the electrons are transitioning, how much energy is being there. And obviously, higher energy or more energy levels transferred results in the total number of energy being higher, and also meaning a shorter wavelength and probably a color closer to that violet side of the spectrum if it's visible. If it's transitioning just a small amount of energy levels, it's going to give off a lower amount of energy, and that lower energy is going to transition to a higher wavelength and more on the reddish side heading that way in terms of the colors that you would actually see. Any questions on that there?
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So again, this is the 4 lines that we see in the hydrogen atom, and that's its line spectrum. Once again, these are specific to, for example, hydrogen. You will see these specific colors come out. You also see them happening at these specific wavelengths. Like I said before, every element will have its own unique line spectrum. So if you were looking at neon's line spectrum, it would look different in terms of maybe not the colors per se, but exactly wavelength wise where they come out. You may have some similar colors, maybe some different colors. If you looked at something like helium or neon or argon or krypton, you would see some different wavelengths happening, maybe some different colors that are the most intense type colors. Once again, each of these transitions and these sort of lines represent electrons transitioning from different energy levels, corresponding wavelength of light that comes off in the visible part of the spectrum. Now, as I mentioned before, Bohr's model of the atom offers a theoretical explanation for those 4 sort of lines that you see in the hydrogen atom. It's a very complex sort of treatment, and we're not going to go into great details. But as I mentioned before, the idea of a theory is it does account for some things. It may not be correct in all aspects. And that is what happened here with Bohr and his model of the atom. It nicely explains hydrogen, but again, doesn't necessarily hold up all that great as you kind of move away from hydrogen, things with more electrons. His model of the atom is kind of like a planetary model of the atom. His idea was you have the nucleus, obviously, and then you have these orbits, he called them. And you have these orbits where electrons were, again, sort of moving around in these sort of rings around the nucleus. The restriction that he had was, again, each of these sort of orbits were different energy levels, like n equals 1, n equals 2, n equals 3. N is the what is known as the principal quantum number. We'll see it in just a second. And an n equals 1 is the ground state. It is the lowest, and it's closest to the nucleus. As you go to like n equals 2, 3, 4, 5, 6, 7, you're getting further away from the nucleus and higher in energy. And so anything sort of above that, and from like 2 to 7 is a higher state of energy. Now, his idea was that you had these sort of nucleus, you had these orbits, and what we are seeing is an electron had to be stuck in one of those orbits, kind of orbiting around the nucleus. Couldn't be found anywhere else. It's got to be there. And if that electron wanted to move energy levels, it would gain or lose enough energy to transition fully to the next orbit. Once again, this is the idea of that quantized energy. It wouldn't find itself in between orbits in this case, just hanging out. It will either, again, lose or gain enough energy to fully make that transition. Same thing if we had an electron down here. If it gained energy, it would gain enough energy to fully make it to kind of that orbit, for example. And that energy allowed to do that is from that equation that we just talked about earlier, that E is equal to H times the frequency. And you can use those equations like we did earlier to calculate the energy required to do so. So his idea was these electrons are trapped in these orbits. They're orbiting around the nucleus. They have to be in one orbit or the other, or gain and lose energy to make it fully from one orbit to another. Again, as they sort of lose energy and go from one orbit to the next, that is what he accounted for as being responsible for what we see in terms of those lines in that line spectrum. Again, um, purple as a result, maybe one transition of one energy level to the next, red one maybe another. So again, as it drops from a higher energy level to a lower energy level, again, the atom's going to emit that energy in the form of a photon of light. And again, in this particular case, it may be responsible for a red that you would see. So in terms of those energy levels, n is what's known as the principal quantum number, and whoops, come back. The principal quantum number, which is n. There's actually four quantum numbers. We'll talk a little bit about the four quantum numbers, just a little bit in this class. We're not going to really go into great detail about them. When you take 1A, you'll go into a lot of detail about them. But the four quantum numbers, the first one is n, which is the principal quantum number. And as I mentioned before, it's really a fancy way of saying basically the energy levels. And that n is equal to 1 is that lowest in energy ground state. As you go above 2 through 7, and n can have values of 1 through 7 basically. And as you go through 2 through 7, they're excited states of energy, and they're higher and further away from the nucleus as you continue up the ladder there. These energy levels, as we'll talk about, is again within the atom where we can find electrons being housed, depending on how many electrons the atom has, as to what electrons and what energy level you may be on. And as we've been talking about, again, this kind of smaller transition of energy going to result in a lower energy and longer wavelength, and we see a red light coming off, as opposed to, say, this guy, where he's starting way up there and transitioning all the way down there. And that's a much greater amount of energy difference. And that larger energy is going to mean that we have a higher energy being released and a shorter wavelength. And again, we see more of a blue light coming off as that transition occurs. Once again, we see these distinct lines in the line spectrum because the electron will not lay up halfway there. It will fully make that transition. So it will either find itself at this energy level or this energy level, and the difference between those energy levels is really a kind of a fixed amount. So as they travel from one to the next, always going to give off that same amount of energy, which means, again, if it corresponds to that blue light, this atom here should always give off that blue light at the same energy and the same wavelength, and would correspond to the same line that you would see if you looked at it through a prism and a line spectrum. Questions on that there? And here's the 4 sort of transitions that we see in hydrogen. And again, each of these transitions correspond to the different colors that we saw. So if you remember, there was 4 different colored lines that was up there. And each of these sort of transitions of energy is a result, are those colors as a result of those electrons transitioning. Again, sort of our idea here, A is our continuous energy, which again is more like the ramp version of walking up a ramp. You can stop anywhere along the way. Once again, atoms, like we've been talking about with the line spectrum, they are forced to be here, 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 or here. And because these energy levels are separated from each other by a specific amount of energy, if an electron always goes from here down to here, it will always give off really, again, the same amount of energy, because that transition is the same amount of energy and the specific wavelength that occurs with it, giving us that line spectrum. And there's our staircase or ramp example we've been talking about. So Bohr's model was really good, like I said before, explaining sort of what's happening with hydrogen. Again, as you get a lot more electrons involved, it doesn't hold up so well. And we moved to this sort of wave mechanical model. And one of the sort of early on sort of ideas that sort of moved us or starts us moving away from Bohr's idea of the atom is one done by a guy named de Broglie. And de Broglie really didn't actually do any research on this. He just theorized it, and it was later proven by people that did research after him. And basically, the idea of de Broglie was this. He basically thought that if light could behave like a stream of particles, why can't particles like electrons also possess wave-like function? And again, it comes back to that sort of dual nature of light, that waves have particle-like function and particles like electrons could have some wave-like functions. So his idea was an electron was bound to the nucleus. So remember, electron being negatively charged, the nucleus being positively charged, there is definitely going to be an attraction between them. And it behaves like a standing wave. So like if you had a guitar and you plucked a string, that string is basically attached to your guitar. So you will have what is, again, a standing wave, right? Your string doesn't leave your guitar, hopefully, right? So it will make the wave that will happen. But it's attached to the guitar, so it can't really move. And that's the idea there of like his idea of those electrons. Maybe these electrons aren't in these nice, pretty orbits, but because they are negatively charged and there is an attraction to the positively charged nucleus, maybe it's like the sort of guitar string, it's like tied to each other. That's why, again, those electrons just don't fly away, right? Because there is that kind of attraction to the nucleus that sort of ties them to the atom, unless there's something much like a guitar string, right? There is a way to separate your string from your guitar. You could like cut it off, right, and pull it off, right? But it takes some effort to do so. By itself, it hopefully will not just pop off, right? So same thing here. Our electrons are tied to the nucleus by this attraction, this sort of wave function that allows them to stay there until obviously something happens that could allow potentially some electrons to leave, but most of them will basically stay there. When we do pluck, by the way, a guitar string or a standing wave, there's a point where there is no amplitude. These kind of spots where there is no amplitude. Remember, amplitude is really the height of the wave, if you want to think about it. These are what are sometimes referred to as nodes. These sort of areas of kind of no amplitude that occurs within the wave. So some points, like I said, are referred to as those nodes. They have no amplitude. And again, he led to the idea that waves can have particle-like functions, and again, particles, much like electrons, specifically what we're talking about, can have these wave-like functions. And because they can have these wave-like functions, this is again kind of moving us away from Bohr's idea of like, hey, these electrons are in these orbits, they're moving around these pretty little circles around the nucleus and stuff like that. The next major sort of development that sort of moved us away from Bohr's model of the atom was one done by Heisenberg and the Heisenberg uncertainty principle. And the Heisenberg uncertainty principle basically states that it's impossible to know at the same time how a particle is moving and its exact location. There's an uncertainty in that. And if you think about really Bohr's model, Bohr's model was pretty much I know these electrons are in these orbits, and obviously if they're in orbits and they're circling around, you could, technically speaking, put your finger there, but hypothetically speaking, and eventually the electron will come back around, right? So it'll come back around. They're in these kind of known orbits and they're moving like this. Heisenberg said, no, 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 because electrons are particles and they have this wave-like function, we don't exactly know where a particle is at any particular point in time, and we don't know how it's moving. And in fact, the more information we have about the location of a particle, the less information we have about how it's moving, how fast it's moving, where it's actually located, and vice versa. So there's always an uncertainty in the sense of the more you know about one thing, location or how it's moving, the less you know about the other. So that makes us has to sort of move away from this idea of electrons are in these pretty little orbits, they're circling around. We for sure know how they're moving, where they're located, to this idea of we know electrons are basically moving around. We also know there's some type of attachment to the nucleus which prevents them from just flying away. But we definitely don't know exactly where they're located to know where they are at any given point in time. The last sort of major movement away from Bohr's model of the atom came by a guy named Schrodinger, and he did a bunch of equations and stuff like that, which you probably will not see unless you take physical chemistry for one semester of it. They kind of do that. But the idea of Schrodinger was because we do not know, based on Heisenberg, right, exactly how an electron's moving or where it exactly is, the best that we could do is think about an electron's location as a probability of finding an electron in a specific location. So we move from this idea of Bohr where they're in these orbits, they're moving around in pretty little circles, I know exactly where these electrons are, to the idea of, nah, I don't really know how it's moving, I know where its location is. The best I could do is like, hey, in this area of the atom, there's a pretty good shot you could find an electron. I don't know exactly where it's at, don't know exactly how it's moving, but if you kind of hang out in this area, you probably at some point will run into an electron. And that's the idea of electron density. Where we have high electron density, there's a higher probability of finding an electron. Where we have lower electron density will be a lower probability. If you think about the atom, again, the nucleus is positively charged, which means around the nucleus would be probably a pretty high probability of finding an electron. I can't really deal with my pen here, but as we move away from the nucleus, the color would get a little bit lighter red as you would move away, and there would be a lower probability of finding an electron further away from the nucleus. Now, even with a lower probability of finding an electron from the nucleus, as you move further away from the nucleus, it doesn't mean you cannot find an electron there. It just you'd probably run across an electron a lot quicker if you were closer to the nucleus, because we know they are negatively charged, nucleus is positively charged, so you will have this much higher probability of finding an electron there. The other major sort of movement away from Bohr's model of the atom was he classified electrons as being in orbits. We do not think of them as being in orbits, and we move to what is referred to as an orbital or an atomic orbital. And an atomic orbital is really a theoretical probability map based on this guy's equations of where you can find an atom within, or an electron within an atom. So the electrons in an atom are found in these orbitals. They're oftentimes called, more formally, they're called atomic orbitals. And there's only certain types of atomic orbitals that we'll talk about here. There are s orbitals, there are p orbitals, there are d orbitals, and there are f orbitals. And these classification of orbitals are, again, these sort of probability maps within an atom, these theoretical sort of shapes, as we will see as well, where there's a good probability of you can find electrons sort of housed within the atom. So once again here, we have now at this point really moved completely away from Bohr's model of electrons are in these orbits to, again, this more quantum mechanical model where we find these electrons in these probability maps known as orbitals. Any questions on that there? Here is such a probability map, and you can kind of pick it up on the screen there a little bit better. You can see, obviously, dead in the center where we would sort of anticipate the nucleus being. I'll just kind of draw a dot somewhere there. You can see it's much, much darker red, which is a higher electron density map. And that means there's a higher probability in that area of finding an electron. Once again, based on Heisenberg's idea, even though there's a really high probability of finding an electron there, we don't know exactly where it's located. We don't know exactly how it's moving. We just know in that area, pretty good shot, you're going to eventually come across an electron. As you can see on the screen there, as you kind of fan out, the color gets lighter and lighter. And again, that represents a lower probability of finding electrons in those spaces. Once again, does not mean you cannot find an electron out there, but it might take you a little bit longer maybe to come across an electron if you're hypothetically somehow standing out there waiting for it to come by. Any questions on that there? So let's talk specifically about these atomic orbitals and where electrons are housed within the atom. Let's start with the first type of orbital, and actually let's start before that, which is, let's start with just in general, any individual atomic orbital, be it a s orbital, a p orbital, a d orbital, an f orbital, it doesn't really matter. Any individual atomic orbital can only hold 2 electrons maximum. So 2 electrons maximum. Pi represents an individual orbital, and the arrows represent electrons. An orbital can only max out one individual one with 2 electrons. Do you have to put both electrons in the orbital? You do not. So it could have minimum of 1, minimum or maximum of 2, or it may actually be empty in certain cases. So there are orbitals within an atom that are empty. There's no electrons in them. But they can have anywhere, obviously, from no electrons in them to a maximum of 2, and a minimum, if you have at least 1 electron in there, that could have 1. Now, when we talk about s orbitals, they actually start at the very first energy level, the n equals 1 energy level. So if you remember, n equals 1 is the lowest energy state. And if you go to the n equals 1 level, you will find a what is referred to as a 1s orbital. The s represents that it's an s orbital. The 1 represents it's on the first energy level. So when you see that 1 in front of the s, it means you're on the first energy level and it's an s orbital. There is only one type of s orbital. So no matter what energy level you are on, there is only one type of s orbital. An s orbital is shape-wise just a sphere. So it's just kind of a circle is the shape, the theoretical shape of it. And you find s orbitals on every energy level. So if you went to the second energy level, you would have a 2s orbital. If you went to the third energy level, you would have a 3s orbital. Fourth energy level, you would have a 4s orbital, and so forth, a 5s, 6s, and 7s as you go all the way up in terms of energy level. So you will always, on every energy level, have a s orbital available to you. Now, because there is on any of those energy levels only one individual s orbital, that means the maximum number of electrons you could put on any s orbital is 2 electrons. So if I wanted to fill this one up, I could only put 2 in there. If I wanted to fill this one up, I could only put 2 in there, and so forth. So again, the maximum number of electrons that you could put into an s orbital is always going to be 2, because there's only one type of s orbital. Any questions on that there? So here's what it kind of looks like.
An s orbital has a spherical shape with the nucleus at the center.
So you can see kind of like a math plane there, X, Y, and Z, kind of in the center there is kind of like the nucleus. And again, all that is where probability of finding electrons somewhere within there. So as you can see, come here. That's our electron density and kind of our overlap of our s orbital probability map. Now, when we talk about s orbitals going from different energy levels, our 1s, 2s, and 3s orbitals, they have the same shape theoretically, but they just get larger to accommodate all the electrons that happen as you go from multiple energy levels. There's going to be a lot more electrons involved. So the size of it just increases as you kind of increase your energy level or your quantum number. Once again, this is a 1s, means n is equal to 1. This is a 2s orbital. You're on the second energy level. This is a 3s orbital. You're on the third energy level there. So again, that number in front of the letter represents what energy level you're basically on. The next type of orbitals are what are referred to as p orbitals. And p orbitals actually do not start until you get to the second energy level. So these guys start at the n equals 2. So you will not find p orbitals on the first energy level, but you will find them on the second energy level and all energy levels after them. Unlike s orbitals, there's actually 3 types of p orbitals on any energy level. There are 3 types. They are known in this case as px, py, and pz orbitals. They are individual p orbitals on a particular energy level. The x, y, and z is like the math little plane there that we just saw. One's on the x-axis, one's on the y, and one's on the z-axis, is where they're kind of oriented in 3-dimensional space. Now, when you have multiple orbitals that are the same on the same energy level, they are sometimes referred to, if I took all these guys together, all 3 of those, these are sometimes referred to as a subshell or a sublevel, depending on the book that you're reading. And that is a collection of the same type of orbitals on the same energy level. So if we kind of fill in our little diagram here, on the first energy level, we have our 1s orbital. When we go to the second energy level, we still have a s orbital, but we then start to see what is referred to as the 2p subshell. Again, the 2 meaning it's on the second energy level, the p meaning it's an orbital, and once again, that represents our px orbital, our py orbital, and our pz orbital, and that is known as a 2p subshell. If I were to fill up the entire p subshell on a energy level, how many electrons can I put in there if I fill it completely up? 6, right? Each individual one could hold 2, and there's 3 different types. So 3 times 2 is 6 maximum electrons if you fill them up. You go 1, 2, 3, 4, 5, and 6. You could fill them up completely. Do you have to fill all the entire subshell with electrons? No, just like the other one. They could be empty. They could have 1, 2, 3, 4, 5, or 6 electrons. But once you hit 6 electrons in that subshell, it is completely full, and you would have to move on. By the way, it continues. If you go to the n equals 3, you have a 3s orbital. 1, 2, 3. You have a 3p subshell present. again, and you went to the fourth, you would have a 4p subshell to the fifth, and so forth, all the way through along the way. We do not use the word subshell or sublevel with s orbitals because s orbital is only one type of s orbital. So we just call it an s orbital. We don't call it like an s subshell or an f sublevel because it's just made up of one orbital, always referred to as a just an s orbital. But here p, because it's made up of three different types, we refer to all of them together on an energy level, all the p orbitals, as a subshell or sublevel. The reason it's called a subshell or a sublevel is when we talk about the n number, n equals 1 or n equals 2 or whatever it may be. That is what is referred to sometimes as a level or a shell. For example, if I was talking about the n equals 2 shell or level, it would be everybody here, right? Actually, let me just do that with. So if I was doing the n equals 2 shell or level, it would encompass everybody that's on there. Which, by the way, if I were to fill up that entire n equals 2 level or shell, how many electrons could I pop in there? It would be 8. Because on the second energy level, we could put 2 there, right? We could put 2 there, which is 4. We could put 2 there, which is now 6. And we could put 2 there, which is 8. So the level or shell means you go to the energy level, and whatever orbitals are there, no matter if they're S's, P's, D's, whatever they may be, if you fill them all up, that would be the maximum number of electrons that you could put in there. Any questions on that there? All right, so here's what the P's look like.
The 2px orbital is in the shape of a figure 8 along the x-axis.
And you can see it's kind of like a figure 8 kind of thing. The idea there is right about there in the middle-ish. In the middle of those two guys is the node and kind of where the nucleus is, kind of where the little figure 8s are on the sides is where the probability of finding an electron would be in there. Here's our Y, which again looks very similar just on the Y.
The y orbital is in the shape of a figure 8 along the y-axis.
And there is our Z.
The 2pz orbital is in the shape of a figure 8 along the z-axis.
So again, each of those could contain maximum 2 electrons, which gives us 6 total when we take it together. And once again, in the kind of those blue lobes is where we would probably expect to find the electrons housed in those sort of structures. As you can see here, these are our 3 p orbitals, and that's sort of like the nucleus if you want to think about it. And again, you can see kind of near the nucleus is where we have a high probability of finding the electron kind of in these areas along the way. Again, you can see even outside of that area, there's a probability of finding an electron, but again, the higher probability in the kind of darker areas in these theoretical locations. The next type of orbitals are d orbitals, and d orbitals basically start on the third energy level. So when you get to n equals 3, that is where we start our d orbitals. And like p orbitals, there's actually 5 types of d orbitals. So if you do that, 1, 2, 3, 4, 5, these are 5 individual d orbitals, also known as a d subshell when you take them all together. Now again, since each individual orbital could hold 2 and there's 5 different types, if you filled that entire d subshell, how many electrons would that be? That is 10 maximum electrons. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 if we fill them completely up. Once again, you do not need to fill them completely up. It can be incomplete. So, for example, our n equals 1, we have our 1s orbital. N equals 2, 2s orbital. That's where we see our 2p subshell. N equals 3, we have our 3s orbital, our 3p subshell, and that is where we start to see our 3D subshell basically first appear. Remember, energy is increasing as we continue up the principal quantum number. As that gets larger, our energy is increasing. By the way, electrons do go into the atom lowest energy to highest. So they fill all the lowest energy levels. So the first thing that would happen is they would fill this guy. Once that gets full, come here, then here, and so forth is sort of how they start to fill the orbitals in the atom. You can see that there's some pictures of the d orbitals there on the bottom. They essentially are like two p orbitals stuck together, except for the last one kind of looks like a donut with a p orbital going through the middle. But again, they're kind of names there, the xy, yz, xz, x squared, y squared, and z squared represent, again, really the axes those guys are on. And here's what they kind of look like in 3 dimensions.
Y-squared orbital has a clover shape that lies in the xy plane and is aligned along the x and y axes. The
3dxy orbital has a cloverleaf shape that lies in the xy plane and bisects the x and y axes. The 3dxy
orbital has a cloverleaf shape that lies in the xz plane and bisects the x and the z axes. The 3dyz orbital has a cloverleaf shape that lies in the yz plane and bisects the y and z axes.
And again, in each of those kind of green orbitals, or kind of lobes, if you will, is where you could find an electron. And here's our donut one.
Squared orbital, shaped like a PZ orbital, with a donut of electron density around the center. It is aligned with the z-axis.
So this one, as you can see, has a lot of electron density kind of hovering around the center there in the donut sort of shaped, along with the density kind of going up and down on the z-axis there. The last type of orbitals that you have to worry about in most classes that you do are f orbitals. And f orbitals do not begin until the 4th energy level. So our n equals 4 is where they start. There's actually 7 different types of f orbitals. So 1, 2, 3, 4, 5, 6, 7. If you took, again, all of those f orbitals together, that is what is known as a subshell or sublevel. And obviously, if we have 7 individual f orbitals, so 7 individual f orbitals, each one could hold 2. That is a maximum of 14 electrons if you filled it completely up. And again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 if you filled it up. Do not begin until the 4th energy level. So once again, n equals 1. We have our 1s orbital. N equals 2, 2s orbital, and our 2p. N equals 3, our 3s orbital, 3p subshell. Our 1, 2, 3, 4, 1, 2, 3, 4, 5, 3d. And then I'll back up here. We have our 4s, 4p, 4d, and finally 1, 2, 3, 4, 5, 6. Yeah, squeeze it in there. 7 for f basically appear at that point. So again, you can see as we continue up the energy levels, we're starting to put more orbitals in. The reason for that is we need more places to basically house the electrons, right? Also, as you saw in that earlier picture of the s orbital, it gets bigger as it continues up because there's a lot more electrons as you go from one energy level to the next to sort of accommodate that. Any questions on that there? All right, we will lay it up there.